next speaker is Aleksandra Gorska, and she'll talk about MOAH and MOSH. Maybe? Yes, the floor is yours.
Hello. Today we are going to talk a bit about MOSH&MOAH. MOSH&MOAH stand for mineral oil saturated and mineral oil aromatic hydrocarbons. These are ubiquitous petroleum-derived food contaminants that can very easily find their way into the food chain through, for instance, migration from food contact packaging, food contact material, from food processing machinery, or simply because of poor manufacturing and storage practices. So in terms of structure, MOSH consists of linear and branched alkanes and branched cycloalkanes, while MOAH of branched mono and polyaromatic compounds. Toxicologically speaking, MOSH are known to accumulate in human tissues, while MOAH are associated with genotoxicity, and particularly the compounds having 3 aromatic rings or more. So recently, the EFSA has highlighted the lack of data on impurities in food additives derived from fats and oils. So we wanted to tackle this gap by gathering data on MOSH&MOAH, as this is a bit our domain of expertise. The routine method for MOSH&MOAH analysis in food involves various steps. So we typically start by extracting the MOSH&MOAH from the food sample, and when needed, we apply some purification step. Then we inject this extract into an online HPLC-GC system with flame ionization detection. And as a result, we obtain 2 chromatograms, one for MOSH, one for MOAH. And to quantify them, we integrate the area below the hump. In our case, for this project, we have preferred to use a more complex system, which is the HPLC GC times GC with dual FID TOFMS detection. And so the goal of my presentation is to illustrate the advantages of working with such a complex system to tackle the request of the EFSA. So let's describe the system first. We start by injecting the sample into the HPLC for a MOSH&MOAH fractionation. So we collect the 2 fractions into 2 fresh vials, and then we can start injecting these samples into the GC. So we start by injecting a first fraction into a cooled-down column inlet. So this is the FID line in large volume. So we can reach up to 500 microliters of injection volume. So this cooled-down column inlet is connected to a tension gap, which is also connected to a solvent vapor exit to be able to handle such high solvent volumes, and to a 1D column and a 2D column, which goes through a cryogenic modulator, and this second dimensional column is connected to the FID. Then we inject a second fraction of the sample into a multimode inlet, so this will be the TOFMS line. The system of column is quite similar, but we don't have a retention gap here. And so once we have performed the injection, we can launch the temperature program. Okay, so which are the advantages of such a system? Let's start by the most obvious one. It is the better structural characterization and easier interpretation of the chromatograms. This first because of the more structured GC-GC chromatograms that we get, and that allow us to first differentiate between possible interfering compounds and our MOSH&MOAH, and also give an insight on the present structures. So here you have an example of a 1D MOAH chromatogram of an emulsifier, so E471, and you see some kind of humps here. So if you're not experienced, you might wonder what kind of hump it is. So actually these are terpenes and not MOSH or MOAH. And so you cannot really conclude on the presence or MOSH&MOAH just in 1D. And it's only by going to the 2D that you see that you have a cloud on the background of MOAH with interfering compounds here. And then additionally, you can conclude that you have some toxicologically potent compound, so MOAH with 3 and more rings. So this is great because it's so better characterize the contamination is one of the requirements and the recommendation given by the EFSA in its latest scientific opinion on MOSH&MOAH. Now, second point which allows for a better structural characterization is that we can exploit the system to remove the interfering compounds. But first, let me give you a bit of context. So as you saw, we often have interfering compounds in our MOSH&MOAH chromatogram, and typically for the MOAH, to remove these terpenic interferences, we epoxidize the sample. So basically, we add an epoxy group to the double bond of the interfering olefins, which make it more polar, and so we are able to separate from MOAH. The problem of this method is that MOAH compounds also contain double bonds, and so they are also partially removed. And recently, we have developed a method which does not employ the epoxidation method to purify, but rather just HPLC. So using HPLC, we have shown that we are able to retain some of these terpenic compounds. So here you have a chromatogram before this purification and a chromatogram after the purification, which give you a clean chromatogram. Whoops. Then third point, which helps also for a better characterization, is that using the same HPLC elution as used for purification, we can separate MOAH in number of rings. So you can get a fraction with MOAH with 1 and 2 aromatic rings, and a fraction with MOAH with 3 and more aromatic rings. So since this separation is performed physically, you can then inject it into the 1D system, and so you can determine the amount of 3 and plus MOAH without being so much dependent on a GC times GC system. Okay, now second point why this system is advantageous. Thanks to the GC times GC and the TOFMS detection, we can identify some specific markers that can help us indicate from where our contamination comes from. So an example is diisopropyl naphthalenes. When you identify those compounds in your chromatogram in presence of your MOSH&MOAH contamination, you can conclude, or at least it gives you indication that your contamination comes from recycled paperboard, so probably some food contact material. Lastly, and this is a new advantage, is that we are able to perform a simultaneous analysis of MOAH and pHs. So polycyclic aromatic hydrocarbons are carcinogenic compounds that are formed during combustion, incomplete combustion of organic material. And they are structurally similar to MOAH, so they are kind of the non-alkylated version of MOAH, but they have very different analytical requirements. And so why so? First, because of the concentration at which we find them in the food matrix. So for MOAH, we find them at level of ppm in the food, while for pHs, we are at the level of ppb. So we have a factor of 1,000 of difference. Second, because of the integration approach. For MOAH, and we integrate as hams. So you integrate the area of all those hundreds of coeluted compounds. Instead, for pHs, you are integrating peaks. So in this case, you can calibrate the response of each of your peaks, while here you cannot. So as a consequence, for quantification of MOAH, you need a detector that gives you a similar response for all hydrocarbons. And so FID does perfectly the job. Instead, for pHs, you need something that is a bit more sensitive and also selective. And in this case, we are rather preferring MS. So this HPLC GC-GC system can help, well, handle both analysis at once, and so analyze both pHs and MOAH. An example here, we have a GC chromatogram of MOAH from a soy lecithin that is spiked at 0.5 ppm of MOAH and 1 to 2 ppb of pHs. You clearly see here the cloud of MOAH, but when you look at the elution zone of the pHs, you don't see anything. So then, of course, we go towards MS, and if you work in total ion chromatogram, you again don't see much, you don't really see the MOAH. The trick is, of course, to work with extracted ions, and here you see the pHs, two of them. Another point I would like to emphasize, we are able to do this simultaneous analysis because we have developed also this purification method with HPLC. So if we were using the usual epoxidation method, we would be losing pHs, so they are not really properly recovered after this epoxidation procedure, while when we apply this purification using LC, the recovery is much more consistent among all the pHs. So let's sum up. The EFSA has highlighted the lack of data on impurities in food additives derived from fats and oils. So because of our expertise in the domain, we wanted to investigate the contamination in MOSH&MOAH using an HPLC GC-GC system with a dual FID TOFMS detection. In the presentation, we have demonstrated that the system is worth this complexity as it allows for, first, a better structural characterization and easier interpretation of chromatograms, and this not only because of the higher resolution of GC-GC, but also because we can physically separate the interfering compounds and the 1, 2, and 3+ ring MOAH using the HPLC. Second, because we can identify some markers helping to find the origin of the MOSH&MOAH contamination. And third, because of the simultaneous analysis of MOAH and pHs, which is something new. So these points would not have been reached without with the routine HPLC GC-FID method. So more complex is not always better, but in this case, it is. So thank you for your attention, and many thanks also to my team, especially my supervisor, Professor Giorgia Purcaro, who is not here today, unfortunately, and many thanks also to our collaborators.